All right, so now we're going to go on discussing a little bit about these galaxies or spiral galaxies other than our own Milky Way. Here are just some nice images of such spiral galaxies. One of them actually taken from the rooftop of our D building where we have our offices. Another one with the Marvel, our Institute's Marvel telescope. You can see a little bit that, yes, in one way we know a spiral galaxy when we see it. I think we can say that, hopefully. But they do come with quite a lot of diversity. You see that the spiral arms here are different than the spiral arms here. You can have more or less prominent bulges, yeah. Sometimes they can be and the luminosity of the bulge can actually vary quite a bit. You have, for example, the famous Sombrero galaxy, where you can Google this, where it's very high luminosity there. And we have already mentioned we can have a bar. Some spiral galaxies have a bar, and some do not, and so forth. An additional thing is, of course, that it depends on in which waveband you look. Then it can look quite different. Here you see 4 different views: X-rays, ultraviolet, optical, far infrared. And in the X-rays, you don't really see it, of course. That's the hot gas. In this case, likely coming from outflows close to the galactic center. In the ultraviolet, you see the spiral arms very prominently, and this again is not surprising because there in the spiral arms is where we have active star formation region. Thus we have the young massive stars that shine a lot in the blue. Hence we see it a lot in the ultraviolet. Yeah? Where if you go to far infrared, you see, of course, the bulge much better, and so forth, if we go to radio. So, yeah. Now, here is just a little table summarizing properties of these galaxies according to the classification scheme. This is the Hubble classification schemes that we have had in the first class. Now, the absolute magnitude, you can see that it goes down, so that these are the irregulars at the right end here, and also the less luminous, the ones with the lowest luminosity, as you can see. Now, in terms of the mass, that of course correlates. These are the most massive ones, the early, or the SAs, and the least massive ones over here. You can see that the luminosity of the bulge, again, decreases with type, yes, until, of course, in the irregulars here, and in these, we don't really have any bulge to talk about. The diameters also, these are bigger, and this diameter here now is given by the so-called D25, and I will come back to what that means. That's a luminous characteristic diameter that we talk about, defined from these type of surface brightness profiles that we had at the beginning of today. Here is the mass to light ratio. As you can see that they are also then higher here at the early SA types, and they go down, and for the irregulars and those, they are on the order of unity. So you can think about this as a measure of the roughly a measure of the active star formation, right? So if you had like a starburst galaxy, that's a lot of star formation now, then of course the mass to light ratio would be lower. And the less, the lower active star formation you have, the higher it will go. So you can associate it with that approximately, right? Here is the Vmax. Vmax in this case is the maximum rotation speed of the inferred from the rotation curves. Yeah. Again, You see the correlation here, right? Opening angle is the opening angle of the spiral arm, essentially how densely packed the spiral arms are. This is the surface brightness. So I0, only it's in logarithmic, it's in magnitudes here. So typical then denoted by mu, right? The central surface brightness. And here you have the interesting result is that they're constant, right? Approximately constant here. This is called Freeman's law, and we will come back to that later a little bit. B minus me, that's how blue they are. So you see bluer here, redder here. Correlates, of course, with star formation then again. Yeah. Active star formation. The total gas content versus the total mass. And how much is locked in H2, that is ionized, versus H1, that is neutral. Okay? Now, for the surface brightness, I already alluded to that this is then in magnitudes measured in mu, right? We had that the bulge, if you go to magnitudes, this is kind of like the Vauquelaire's law put on a logarithmic form, right? So you have the 1/4 here with the effective radius, and that's a better fit than for the bulges. For the discus, it's often an exponential, so this becomes this in logarithmic form with the scale length that we have already discussed, right? But remember also that you could sort this out approximately in the same type of law, and that was then called the Sersic profile. You go back to module 1, look at the introduction of the important concepts there if you have forgotten what the Sersic profile is. And that will actually also then come back to us next week when we discuss, so to say, statistical properties of the galaxy population as a whole, yeah, and how to classify this. Yeah. Now, I mentioned Freeman's law already, and that is the empirical observation that the central surface brightness of spiral galaxies have very low spread, and it's around this 21.65 mean value for the classes to the left in our diagram. Yeah. Of course, this was Freeman 1970, yeah, and there was a selection bias here. Disks with higher surface brightness were, of course, easier to detect. So there is a certain selection bias but empirically this has played a very important role in the characterization of the spiral galaxies. Now, I will mention, though, that there is another class which doesn't follow approximately this Freeman's laws, and they then called low surface brightness galaxies, and that's exactly what it sounds like. They have, for a given luminosity, much lower surface brightness than indicated by Freeman's law, hence the name. And it may be a separate class of these galaxies. They're 2 or more orders of magnitude lower than predicted by Freeman's law. And that's actually lower than the brightness of the night sky, which means that they're difficult to detect, obviously, because you have to be very careful with the night sky subtraction there in order to detect them. Kind of like in the same way as it's difficult to detect dwarf galaxies. That's what I mentioned before. Now, one of the important things with the low surface brightness galaxies is that they're believed to be dark matter dominated also in the inner parts. Now, if we look at the standard spiral galaxies, then when we go to the disk and to the inner parts, we're not completely dominated in those regions. You can, so to say, hint that from the rotation curve also, by the dark matter halo anymore, which means that it's difficult to get constrained on the dark matter properties in the inner regions. And why is this important? Well, it has to do with this so-called cusp core problem. One of the reasons why it's important. The cusp core problem we alluded to again last week when we discussed the properties of dark matter halos. Remember that when we looked at the isothermal sphere, right? Then we had one solution which we call the singular isothermal sphere, which went up to essentially an infinite density at r equals to 0. And that was a solution to the equations. Okay. Now, obviously, we have to truncate it, and we discussed various ways to do that, right? But if you look at the numerical big simulations of dark matter halos, you see that the density actually increases quite steeply also in the very innermost regions. Okay? This is most easily interpreted through this NFW, the Navarro-Frank-White analytic approximation to these numerical simulations, where you see that the density at the innermost regions actually still goes up with 1 over r, right? So it's not 1 over r squared as in the singular isothermal sphere, but it's still very high. And this is what we call a cuspy inner regions. Whereas observations then typically indicate that no, the galaxies, they are more core-like. That is, that they don't exhibit this steep increase in density or in surface brightness as we observe them in the innermost regions. And enter then the low surface brightness galaxies, because if you can observe them, they are believed to be dark matter dominated also in the inner parts, so you can get constraints also on the dark matter component in those parts, which is not easy to do from, say, normal spirals, because there it's the luminous matter that dominates, so you don't know what the dark matter component, but here you do. And so far, the last I checked, I should say, there seemed to be no indications that we really had these type of cuspy cores that are predicted by the dark matter halo simulations. So this seems to remain an issue in the standard model. Here is such a surface brightness plot. So this is the logarithmic surface brightness now as a function of then radius inferred for a galaxy. And you can see here is the fit, but then you can see that in the bulge, in this case, it goes up, and the disk sort of say saturates here at Freeman's value, but the bulge is, in this case, over luminous, as we call it, okay? It follows a different law, but it has a higher surface brightness than would be predicted if you just extrapolated the exponential disk to the Freeman's. And this is often the case, it's not always, but this you can often see, Now, another point here is that you can see that the sky, in this case, is 22.3, right? So that would be on the order of here, right? That's the sky subtraction. So then, of course, if you were at Freeman's law, 21.65, I think it was, and then you take a low surface brightness galaxy, which had 2 orders of magnitude lower, right? Then you would, at the central part, still be down here, so below the sky limit. So that's why they're difficult to detect. And you can also see here that, okay, so if you want to infer the total luminosity here, you're going to have to cut off. Where do you actually cut off the what do you call the luminous radius of this galaxy? As you can see, this is actually not very so trivial, right? So in the center we're 100,000, but the outer radius is like less than 1% of the sky brightness. So fits are often used to derive then the luminosity within a certain radius, and in analogous then to the simple exercise we did at the beginning of the class. Okay. Now, when we talk about the galaxy radius, the size of the galaxy in the table, you remember I alluded to is R25 radius. And this R25 radius then is simply defined as the radius where the mu magnitude is 25 in the B band. Okay? So in this case, that would be the characteristic visible radius of this galaxy. Now, there are also other ways to characterize that. For example, the Holmberg radius, that's actually at 6.5, right? So that would be a little bit further out. In this case, etc. So the sizes of galaxies, they're often given out to some specific isophote in this case, right? So that also then can give us an estimate of the outer visible radii, yeah, and the outer visible mass. So if light then followed, yeah, if matter then followed the light distribution, the rotation curve should not remain flat outside this radius. This is what we have now been coming back to several times. So hopefully we understand the reasoning behind that now. Now, in the observations though, this is not what we observe, as we already know. The rotation curves of spirals, they typically remain flat to well outside the Holmberg radius or the R25 radius, right? As illustrated by just 3 different examples here, where you see that it remains flat out to say 40, yeah? And you can also see this is analogous to the stuff I was showing you before for the Milky Way galaxy, right? Where you have some sort of gas contribution, disk bulge, dark halo. The dark halo in this case is the dashed dotted, right? So it's this one. And if you don't add the dark halo, you will not be able to match the observations here of the spiral galaxies. Yeah. And a very similar result is then obtained if you were to say, okay, I want better data, so I were to just stack a lot of observations to get one big rotation curves. Yeah. And yeah, that means that the total mass of spiral galaxies is very often unknown, right? Now, typically we can put the number, we talked about the Milky Way, likely like 10 times or something like that, times the mass contained inside the solar radio. Yeah, that's a typical number. Sometimes you talk about, well, we don't know how it is, but it's more than 4 times the visible mass, etc., etc. So those are the type of reasoning that you can do, because as you know, as long as this remains flat, the mass is still increasing. Remember the 1 over r squared dependence in the isothermal sphere. Remember that the mass then continues to increase with radius. Then we don't know. It has to drop somewhere, right? But it is a useful reminder that we seldom observe this. So the next context that I wanted to bring up when it comes to the disk galaxies is the so-called Tully-Fisher relation. This plays an important role, as we will see in the next slide, in the astronomical distance ladder. Okay. Now the Tully-Fisher relation, is actually an empirical relation between the total luminosity and the maximum rotation speed of the spiral galaxy. Okay, the maximum rotation speed you can infer in different ways, right? But the important thing to remind here, why it's also useful as a distance ladder, is that you can do that then also for unresolved objects. I mean, for unresolved spectral lines, as inferred here. So these are 21 centimeter lines for unresolved 21 centimeter observations, where you see that you get then not one from different parts of the galaxy now, right? Like in the detailed rotation curves here. We have to have, say, if we do this with the 21 centimeter line, right? We have to have one observation at this radii. We have to have another observation at this radii, another observation at this radii, etc. So that we have to have resolved 21 centimeter observation from here, or well, in that case it will be from here, and so forth, right? Yeah. But here we're dealing with one unresolved observation from this part. Yeah. And then you measure the total line. And then you look at, okay, how broad is this line? And then, of course, that broadness then is associated with the maximum rotation curve, in the sense that if this galaxy were rotating in this way now, right, then this part would be maximum redshifted, this part would be maximum blue shifted, and then you could just read off those values down here. This is now put in velocities, right? So you just use the Doppler formula. You have to correct for the motion, also of course for the galaxy. And then you measure the width. You get the total velocity width, and you relate that to the rotation, maximum rotation speed of the galaxy. This is analogous to, for example, how you derive projected rotational speeds of stars as well, right? You don't use the 21 centimeter line for that though, but that's a that's a different story. All right, here is the empirical Tully-Fisher relation, where they discovered that if you put this in magnitudes or in luminosities then you follow an empirical law, which is a power law in the rotational speed, where a power index is on the order of 4. Yeah. Now, if you can calibrate this now, then you get a distance ladder. And why is that? Well, if you can just take the observations there, you get the maximum speed. Okay? From that maximum speed, you can directly read off this is the intrinsic luminosity or absolute magnitude of this galaxy. And then you have measured the apparent luminosity. Then what do you get? The distance, if you can correct for extinction, and if you have a well-calibrated relation, right? But this is exactly how it's used in the as a distance ladder, the Tully-Fisher relation. Now, I should say that this again is an empirical relation, and perhaps there is not a again, to my awareness, there's not like a model that can, from first principles, really explain the Tully-Fisher relation. I'm trying to put it carefully now. But we can understand it from, perhaps from some basic scaling relations. And that is, this is just the rotational curve that we had in the beginning, right? So if you just rearrange it, you see that it's this ratio that should be a constant for the rotational speed. Yeah. And then you just take the luminosity, you expand it a little bit, and you use this then relation to get to this. Yeah. Then you use the relation between the surface brightness and the luminosity. Again, we had that in the exercises at the beginning of the class. Yeah. And then you just plug it together and you get to this, that the rotation speed to the 4th power could scale with the luminosity, but then you have some more factors here. You have the surface brightness there in the denominator, and then you have the mass luminosity relation. So in order for the Tully-Fisher relation to be explainable by this simple scaling analysis, you will have to invoke that spiral galaxies has a constant surface brightness, central surface brightness. I should have inserted here. But that was the empirical Freeman's law, that was actually seemed to be absurd, right? So that's one clue to why this Tully-Fisher relation actually works, you know, whether we can fundamentally explain it or not. Now, the other thing is that the mass to light luminosity has to be constant. And that's not really the case, as we have seen across the different types of spiral galaxies that we observe. So this is a little bit more of an issue, but approximately constant for a spiral galaxy, perhaps. So a small correction factor in this case. Yeah? To explain the Tully-Fisher relation used in this context. Now, at the end, I wanted to come back to our thin and the thick disks, just showing you some recent results revealed by Webb, by the paper by Tsukui here, where they have observed until high redshifts now, so 2 and 3, disk galaxies, and then analyzed the properties of these disks. And they have done detection of single disk to a redshift of 3, and of a double disk from 2 disks, you know, a thin plus a thick, until a redshift of approximately 2. And here you see some very nice disk galaxies reviewed in that paper. Here you see the kind of like fits that you can do, where the data is here, and here you have a model where you have a thin and a thick disk that you fit to your observations, and this should now be a little bit familiar to you. And then you see that you get the surface brightness, and then you add the disk component, and you get the one plus the other component in order then to match the observations. And in this case, here they have just collected their results where in look-back time now. So instead of taking that redshift, we take it at look-back time. So you have to reverse it, of course, then. This is 12 gig a year, so this would be early. 0 would be today, right? And here you see that the double disk fraction goes down until around here. So this is why they claim to see the single disks until the redshift of 3, the 2 disks until redshift of 2. There are, of course, observational biases here, so I don't think that you could claim that this is a final result in that sense. But their main conclusion is that the first disks that they see, they're basically thick disks in their argumentation. In the sense that they argue that the thick disks form first, which is actually a bit contrary to some of these suggestions that I took up when we discussed the thin and thick disk in the Milky Way, right? So that the thick disk with high velocity dispersion forms first, and then you sort of settle down coincidentally to a thin disk. While, for example, external processes such that, you know, you're eating a neighboring galaxy, as we discussed there, and that also then contributes to your disk, can play a role in according to them, can play a role in certain cases. It does not seem consistent with their data as the general explanation here for the thin and the thick disk dichotomy. All right, that was actually what I wanted to say for the lecture parts today. Now, next week we're going to move on and we're going to talk about ellipticals and dwarfs and also the statistical population and distribution of galaxies then. This is actually a spiral galaxy, but you see three of the dwarfs, yeah, of the Andromeda galaxy. This is an image of the Andromeda taken by another old student in the course who was also an amateur astronomer. And the exercises here, of course, are the two that I put already on the slides today, so we will do those. It was the scale height, so we're going to discuss how to relate again the hot disk and the cool disk and the velocity dispersion to the inferred scale heights. Yeah, and then we're also going to review a little bit about the 21 centimeter line of that. All right.